This is the second part of the introduction to the course M7033T Scientific Computing with Applications in Tribology. And it's about the motivation and a little bit on the incentives for learning in this course. My name is Andreas Almqvist, and both me and my PhD student Kalle Kallerin will teach in this course. So, why do we model and simulate in general? Well, there is a saying that nothing is as applicable as a good theory. But there are other ways of seeing this, and one is to see it like a cheap complement to experiments. And what we mean by this is that it's both cheaper, it's faster, and hopefully it's also optimizable. And we can really benefit from having some at least preliminary results from simulations before we set up a very costly and dear experiment to test it in real life. However, to be able to simulate the performance of a complex assembly of machine elements, like in this case we have seals, we have gears, we have rolling bearings, we have splines and journal bearings, we need feasible interface models. There are many fields in machine elements: bearings, gears, mechanical seals, and then we have sort of a glue named tribology, which is actually the study of what happens inside the interfaces between component parts in these elements, machine elements. Needless to say, these interfaces look differently in these different type of machine elements, and we need different type of tribological models to better understand and predict the behavior of a specific one of them. We all know that modeling and simulation is widely used and frequently used in fields as structural mechanics, fluid mechanics, solid mechanics, combustion processes, and even complex things like collision and crash studies and weather forecasts. But what about tribology? In the field of tribology, there are only a few commercially available packages, and I've listed some of these here. ADL has an Excite piston and rings package. Ricardo suite is also focused bias to the automotive. MIT consortium is also a set of tools which are applicable for example, understanding the lubrication of piston rings and cylinder liners. And then we also have a more generic type of software, COMSOL Multiphysics, which since now quite a few years back has this lubrication shell, which Luleå University of Technology has been part of developing. The reason for that it's not so widespread as in tribology as in the other fields is maybe because there are so complex processes. They are stochastic and not deterministic, for example. They are multidisciplinary, and there is a lack of understanding about the fact that tribological problems limits the functionality in life as often as structure mechanics related problems. So while many engineers they focus on the structural mechanics and solid mechanics, they miss completely the tribological aspects, which actually can be the first determining factor for a malfunctioning. So coming back to that there are only a few commercially available packages, I mean, this is also one reason that it's not so widespread. And we all can all cry about that, but we can also be quite happy because we know there is a lot of research to be done here to establish good interfacial models so that we can actually simulate these systems much better, considering also the tribological aspects. The physics going on in a tribological interface spans over decades and decades of length and time scales, and it spans all the way from the atomic level, quantum mechanics, where you simulate or predict energy and probabilities, uncertainties that the atoms are at a certain place in a certain time. It works its way up via atomistic and molecular modeling. For example, molecular dynamics is quite frequently applied nowadays to study formations of tribofilms and such. And then the mechanics of the tribofilms and how they are formed can also be on a higher level, higher scale, in which we consider the flash temperature and fracture and such effects on how the tribofilm builds up. Then further up on the length scales we have the continuum models, such as the fluid, solid and contact mechanics models. And then even higher than that, we look at models that predicts efficiency and service life. So they are comprised of many small constituents, probably both fluid, solid and contact mechanics models, and also perhaps tribofilm mechanics models and so on. And in this course we are only focusing on the continuum scales of the models. So, as an example, how can we predict friction in a rolling element bearing? You can see the rolling element bearing here, and there we have an enlargement of what happens between the roller and the inner ring, the raceway on the inner ring. So they may be moving different speeds due to acceleration of the roller when it comes into the contact here, and the shaft, driving speed of the shaft. And we all realize that we need a model which is of multi-physics nature and considers all the effects that are going on inside this interface. Here we see a schematic illustration of the physics involved, and the figure here is taken from the review paper by Antonis Vakis et al. And there were many of us. I was one of them, but I think we were in total about 20 authors of this paper. We realized that it will be very difficult to consider all of these different physics in a model and simulate the actual happenings in the interface. What we can simulate, at least to some extent, here is wear, it is how the surfaces heats up due to friction. There are models that look at crack growth, and there are of course a lot of models that are devoted to the lubrication aspect, so whether the lubricant can actually form a separating film between the surfaces and protect them from wear, and so on. Performance indicators which we could and should simulate when we have, and if we have, feasible and applicable interfacial models are, for example, lubricant film formation, which gives us an idea of what the risk of wear is, the stresses inside the opposing surfaces, but also the shear stresses inside the lubricant film, the flash temperature, which not only heats up the surfaces, causing chemical and physiochemical reactions, creating these tribal films, but also the temperature in the fluid, causes higher temperature in the fluid, which in turn affects its viscosity, which changes its lubricant film formation, and so on. And friction is of course another very important performance indicator, which we can make use of to estimate the power losses and the efficiency of the model. Wear, and here we talk about both the two-body abrasive wear and two-body adhesive wear, and then we have three-body wear, we have fatigue, and there are many very difficult aspects in simulating wear, but it's of course a very important performance indicator in tribology. There are two main categories of models, and those are the in-contact type of models and the no-contact type of models. If we go from the full film lubrication side where we have no contact, then the load is supported by hydrodynamic action, which means that the load is actually carried by the fluid itself. And this is full film lubricated devices such as fluid film bearings and rolling element bearings. When we approach contact, we have a little bit of subcategories, because we differentiate between what is mixed lubrication and what is boundary lubrication. With mixed lubrication, we mean that the load support is partly due to the hydrodynamic action, separating surfaces a little bit from each other, but still there will be direct contact and load will be supported by partly mechanical action. And then going further into the boundary, closer and closer to more and more real direct contact, the load is supported directly by the asperities, and the fluid has negligible influence here on load support. It can still provide very vital things to the contact, namely the additives in the fluid, which hopefully can generate tribofilms that protects the surfaces from wear. When we see this division of in-contact and no-contact models, it is very typical to introduce the Strybeck curve. The Strybeck curve was obtained by Strybeck himself for a journal bearing, and he was interested in capturing the friction for a journal bearing, and found that if he plotted the friction coefficient as a function of the Hersey number, a duty parameters also called, where we have the dynamic viscosity eta, we have the relative speed between the surfaces u, and p, which is a measure of the load in the contact. And then we can see if we, for example, operate the journal at a seemingly high speed, relatively high speed, we are in the full film regime, where we have full separation between the contacting surfaces. No contact occurs. If we now reduce to speed, we move into the mixed lubrication regime, somewhere where we get actual direct contact between the surfaces. And then if we turn down the speed even further, we move along this curve and we're in the boundary lubrication regime where the friction is highest. Still, it may be seemingly or relatively low for a lubricated steel contact. It's typical for an oil lubricated steel contact. It's typically around 0.1. Let us now have a look at the simulation results in comparison to measurements. So here we can see a hydraulic engine or motor in which a piston is pushed against the cam curve and contact is actually made by this roller which sits inside the piston, and this is lubricated conjunction over here, which is sort of a bearing. You can think of it as a journal bearing, and this is a non-conformal lubricated contact, which is rather typical to that of a rolling element bearing. But if we focus on this contact, we can see here to the left we have a figure displaying the friction coefficient, at least the relative measure, against the Sommerfeld number, which is similar to the Hersey parameter. And here we can see the CAD and some color map displaying the pressure distribution within this flexible journal bearing, so where the roller is contained. Okay, and what we have here on the axis, well, within the axis, is a number of curves. One of them, the dotted lines, are the experiments, coming from the experiments. And as you can see, they follow this typical Strybeck-like curve. And then we have 5 different simulation results, which have, I mean, trend-wise, they all look like Strybeck curves. But if you look at the difference here, for example, in this regime, where it comes from full film lubrication and it approaches boundary lubrication over here, we have a quite big discrepancy between the simulation results. And this is because these simulations results have been obtained from running the thin film approximation, solving the Reynolds equation for this flexible bearing, but with different types of surface topographies as input. So we have measured surface topography here at the bearing surface and use that as input for the numerical simulation, and therefore obtain 5 different curves. And it's really difficult to tell now which one should we use, which one is the most representative. Looks like it is the green line partly, but then over here it's probably some of the other ones. And this is research question still to be answered, actually. Overall, we can see that we have very good agreement qualitatively, but quantitatively there is quite a mismatch and quite a lot more to do to improve the numerical simulation and prediction from those. We have also been looking into engine friction, and more precisely the friction that comes about from the reciprocating action of the piston rings inside the cylinder liner. And Marcus Söderfjell was PhD student. He defended his thesis in 2017. He actually built a floating liner test rig. So here is the cylinder liner, an electric motor that drives a 6-cylinder Volvo engine with 5 deadweight pistons just to get the same type of load on the test piston as this one is for a heavy duty diesel engine. It is much heavier, of course, than for this 6-cylinder automotive Volvo car engine. Marcus also built a virtual test rig. And with this virtual test rig, he, for one thing, was examining the effects of surface texture. So here I have implemented some artificial dimpling on this liner. And these were modeled in different layouts, an inline layout and a zigzag layout. And then these were like this is the mathematical representation of those textures, circular dimples. But then on this seemingly smooth plateau, we also imposed surface roughness, namely the plateau honed parts of roughness as we can measure in a cylinder liner. And this is the typical size of the dimples that was studied. And by including the dynamics, we were able to show that the total friction, actually it's varying, of course, as the piston slides over this inline pattern of dimples. It will see different gap size, and it will feel a different amount of mixed lubrication as it passes over here, and therefore the friction coefficient will vary, or the friction force will vary. But it will actually, the total friction force will actually be lower than the untextured friction force at all times, and this is because of mixed lubrication. So these dimples, they relieve the ring from some of the direct contact, and by that it reduces the friction. May of course increase the wear, but that's another story. Andrew Spencer, he was also investigating the piston ring cylinder liner friction, and he was making use of our Plint machine, which we have in our lab, and it's a reciprocating device in which he mounted and lined up piston rings, and he had cut out pieces from cylinder liners, and then he rubbed these piston rings against the cylinder liners in the Plint and recorded the friction. He also, of course, solved the model, a representative model for this case, and he did that for different measured roughness. As we can see, we have different piston ring roughness here, and we have and we have one specific piston ring geometry over here. So let's see. This is how the comparison between simulations and experiments came out. And we can see again that we quantitatively do not have very precise or very high accuracy on the comparison, but qualitatively they compare pretty well. Andrew was also showing that it's very important to model the whole ring pack, and this puts quite high demands on your modeling, and you have to enforce force balance for each of the piston rings, and you have to record the fluid left behind, and which is the fluid that the next ring will ride on, and so forth. and then it goes up in one direction, and of course the ring pack leaves a different amount of fluid when it goes up than when it comes down. So he was building this model in order to try to investigate how the oil was distributed over the surface, the cylinder line surface. This was a master thesis project, quite recent. One of the tribal students was doing it, and it was in cooperation with Sandvik, and they had these big cone crushers, and these can be, I mean, it can be 20 meter high, and the whole shaft and the whole body of this crusher, which crushes ore, is supported on this bearing, on this step bearing. And he was investigating, well, the lubrication performance of these step bearings with different types of patterns. And well, the results here on the right shows that we have a shallow groove design, which generates a pressure distribution looking like this, and then if we have a deep groove design, it will generate a pressure distribution looking like this. And what you can see is here's the hydrodynamic pressure, so here's the fluid pressure, and here's the asperity pressure. So in this case, the hydrodynamic pressure is actually, perhaps it's not very well seen, but it's lower than in this case, because here the full load is supported by the hydrodynamic pressure, no load is supported by asperity pressure, but here there is a partitioning, load partitioning between what is supported by the fluid and what is supported by direct contact. Francesc Perez-Ravols, he was studying leakage in seals, and he developed the stochastic two-scale models in which he could include the effect of the micro scale into the macro scale of the seal. And here are two cases showing different types of local scale geometries or topographies, and different types of global scale topographies too. And the red arrows here illustrate with the leakage paths. And you can see, for example, here where the leakage is large, it looks like this on the micro scale. In this case, the leakage is much more meandering, and it just loops over these are ridges, they are turning grooves actually. So it can just jump over the turning grooves at certain places where we have the large pressure drops, and then the leakage on the microscales look like this. He was also able to include the history, the loading, unloading history. So if you load this seal, you will probably plastically deform the surfaces, and therefore when you unload it, you can release quite a lot of pressure, but still you will not generate so much leakage. And this is of course important when you design your seals, to know if you have a preloaded seal, how much can the load fluctuate before you see a great leakage occurring. And you can see that behavior is different from these two situations. Another experiment we did was to try to develop an extremely fast friction prediction for a system like this, namely a ball on a disc, or if you like, a ball in a ball bearing. And the target or the objective for this project was to actually develop such a model which should be able to predict the friction in less or down at microsecond level. And to do that, of course, we need approximative models. We need quite a few physics to accurately capture the friction in this device. But we also need to simplify it a lot. So instead, for example, of solving the fluid mechanics problem for obtaining the pressure in the fluid film, we approximated that with a Hertzian contact pressure. And then one may wonder, how well would this model predictions then resemble what we can actually measure in the WAM machine? So let's see. And here we can see the prediction versus the experimental results. And for example, at quite low or reasonably low entrainment speed, we have, and for a certain load also should be mentioned, this is 80 Newton, we have almost perfect overlap of the predicted friction with increasing slide to roll ratio. So more and more sliding going on from 0 to 1 here. The slide to roll ratio is defined like this. And we have almost a perfect overlap. And although the overlap is not as good here as the velocity is high, because this is a pretty high velocity in this type of device, we can see that the difference is not tremendous. And again, we qualitatively we have a very, very nice comparison. This is actually quite sophisticated, quite complex type of model, but I believe the next one will be even more complex. Let's see. So, looking at wear simulation. Here to the left we have a hydraulic motor, and the rim there is in the black, and when you turn the star wheel, the counterclockwise direction around its center, the small green dot here, it will actually rotate clockwise within this rim, and it will make contact at certain places. And there we will have both, hopefully we will have both lubricant there and perhaps a tribal film, but even so it will wear. And the company that Joel Furustig, formerly Anderson worked with, they made a test trick resembling this configuration, and they measured the friction, and you can see 3 different experiments. They are of course not perfectly overlapping, but they give you statistically approximately the same trends at least. And then you can see Joel Furustig's prediction here in red, which is of course it's not quantitatively correct. It's shifted here, and well, it misses some very important peaks with this shift, but still we can see it seems pretty well capturing the behavior of the wear in this hydraulic motor. Before you will examine this hydraulic motor and the wear model, adapted the wear model for that, he was doing a lot simpler, more fundamental type of wear experiments. So he took an indenter in our lab and made small indents in a surface, and then he wore that surface in one of our test rigs, and he measured the wear. Well, he measured the topography before and after, and then he found that the wear volume, he found out that the wear volume looked like this. So there is a certain wear depth, you see 0.3 micrometer here on this very small patch, and these are very small marks, as you can see. Then he also simulated the same thing, and he found out very similar wear, numerically predicted, as he had observed in the experiments. So wear predictions, they can be at least qualitatively very well comparing, but quantitatively we have some more steps to take before we really can be as accurate as we want to be. Joel Furestig did not only simulate wear, he also simulated tribofilm formation by means of adding an Arrhenius type of equation to his model to consider the tribofilm buildup. And he was able to carry out some calibrated numerical experiments, and they were, of course, there were these parameters reversed engineered from experiments, and these experiments, they were made by another PhD student, an industrial PhD student, which was at that time at SKF ERC in the Netherlands. Okay, here's pretty rough comparison between simulation results. See, 1500 meters distance is over here, okay, and 1500 is over here. I could have made a better effort to make these graphs overlap somewhat more, but I think you see that we capture the trends, but of course not the exact values. I hope that you now realize that there is quite a lot to do, and even though we have done a lot in modeling simulations, there is a lot still to be done. And I would say that the trends in modeling and simulation within the field of tribology is towards finer scales, and actually the coupling between the scales. So here you can come in and develop new models and new simulation methods to capture all the effects that are connected and combined of all these scales. And with that said, this second video lecture of this course is finished, and since this is a video lecture, you cannot ask me questions directly, but if you like, you can email me, or we can talk, hopefully talk to each other in the corridor when we meet during the course. Thank you.